Hi, good people, and welcome to Statistics. I wanted to get started right on day one with some interesting math, and I think this is a great problem that we can use to get into this. There's two main types of statistics we're going to learn about this year. The first is called Descriptive Statistics, and the other is called Inferential Statistics. The first month and a half, or maybe 2 months, we're going to be focusing on descriptive statistics, where we collect and analyze categorical or quantitative data through a variety of ways, and we learn some effective methods for drawing accurate conclusions about that data. And we're going to get right into this problem so you can see an example of what we'll be doing just in the next week or so. So this is from an actual study that was published in a article in Science magazine in 1975. They explored the graduate admissions data at UC Berkeley for evidence of bias. And when we first examined this data, there appears to be some clear bias. So let's take a look at what this says. We see that there was a total number of 2,165 men who applied to their graduate school. Out of those 2,165 applicants, 1,022 of them were admitted into the graduate school. So we can just calculate a quick percentage here. That is roughly 47% of the men were admitted. And let's see how many females were admitted. Out of 849 applicants, 262 of them were admitted into the school. So we have, what percent is that? We have roughly 31% of the females were admitted. So there's right away some clear evidence of a bias between the rates at which these two groups of people are being admitted into the school. And that's what was indicated in the article that was published. But upon closer examination, something else begins to emerge, and I want to do that now. So out of the 825 men that applied to, let's say program 1 is the School of Engineering. Out of the 825 men that applied to the engineering program, 511 of them were admitted. That's 62%. Out of the 108 women that applied to the engineering program, 89 of them were admitted. Let's see what that is as a percent. That's 82%. So in this program, let's say it's the program of engineering, the School of Engineering, there actually seems to be a strong case that they're accepting women at a higher rate than men. All right, let's look at this next instructional program. Suppose this next one's the School of Chemistry. These are people applying to go to grad school for chemistry. 352 men were accepted out of the 560 who applied, and that's 63% admittance. And we have 17 females accepted out of the 25 who applied, and that's 68% of them were admitted. So again, there's evidence in favor that females are actually being admitted at a higher rate than males. All right, let's take a look at this next school. Suppose this next school is the law school. 137 men were accepted out of 407. That's 34%. And 132 women were accepted out of 375. That's 35%. Interesting. So women are also being accepted at a higher rate to the law school. All right, let's take a look at this final. Let's suppose this last one is the med school. 373 applicants, only 22 were accepted. So that's a acceptance rate of 6%. And 24 females were accepted out of 341 who applied. That's a acceptance rate of 7%. So what's interesting about this data is that upon our initial examination, we saw that men were being accepted at a higher rate than women, 47% versus 31%. But if we analyzed it within each instructional program, we saw the opposite. We saw that women were actually being accepted at a higher rate in each one of those instructional programs. This has a name. We'll learn about it in Chapter 2. It's called Simpson's paradox. And there's an issue here. There's a confounding or lurking variable. The instructional programs have different difficulties to get into. And it looks like men applied in greater numbers to the ones that actually were less selective and easier to get into, and women applied in much greater numbers to the schools that were much harder to get into, like the law school and the med school. And because of this, this paradox arose, and we ended up making an incorrect conclusion. And this happens quite frequently when you're looking at descriptive statistics. It's important to not draw conclusions before fully analyzing the data. And if you're ever looking at a table like this, it's important to delve deeper, and we'll learn what that's called. These are called contingency tables, and we're going to be finding what's called the marginal distribution, and we'll learn the vocabulary for dealing with that in this chapter. So I thought this was an interesting example to get started with. I want to just show you another quick example of this in case you want to see one on your own. And I won't actually tell you the lurking or the confounding variable in this next example. Perhaps you can try to figure out what it is on your own. Again, the issue in our example here was that engineering and chemistry were actually much easier schools to get into than law and medicine. Men were applying to those schools in greater numbers. The med school and the law school were harder schools to get into, and women were applying to those schools in greater numbers. And that's how this paradox arose. So here's another example. You can read it. This is actually, again, a real-life example. Whenever possible, we're going to try to use real data in this course. Sometimes we'll be pulling it from studies that are published. Sometimes we'll be collecting the data on our own. Here you go. 2 different treatment options were analyzed for successful treatment of kidney stones. And we have treatment A and treatment B. Overall, the success rate for treating kidney stones with treatment A was 78%. Overall, the success rate for treating kidney stones with treatment B was 83%. So it looks like this one is the better treatment option. But upon closer examination, you're going to see something weird going on. And I will let you think about that one. I'm not going to get right into what that is. But thank you for watching. I hope this gives you a bit of an idea of some of the stuff we'll be doing the next couple weeks. And I will talk to you in the Google meeting.